So, cool. So today I want to talk to you guys about photons. My philosophy on talks is in 10 minutes, you can, in like a 10-minute APS style talk, you can convince somebody something is a good idea. And kind of like these half-hour talks, you can kind of tell a story and maybe somebody can walk away learning something. So I decided to give it a very story themed with one photon, two photon, red photon, blue photon from Dr. Seuss's One Fish, Two Fish, Red Fish, Blue Fish. And instead of Dr. Seuss, it's by Dr. not quite yet a Dr. Pearson. So throughout the series, you guys have been kind of given a brief introduction to quantum mechanics and, the thing that the Avengers used to like solve time travel and go back and beat Thanos, and movie broke what almost $3 billion at the box office. But often quantum mechanics is really the physics of the very small and the very cold. And the term cold is a relative term. And seemingly continuous things are discrete. With atoms, we have matter, we have atoms, energy, and today we're going to talk about light. And light exists as something discrete that we call photons. And I'm sure through all these talks, especially at the beginning, you've probably talked about wave functions, the importance of measurement and the implications of measurement, the property of superposition, where qubits live as a superposition of two states, 0 and 1, and spooky action at a distance, entanglement, a very quantum effect. So if I'm going to talk about photons, I should probably, discuss what is light, something that's kind of plagued philosophers and physicists for centuries, if not millennia. And I'm going to jump all the way ahead to really the 17th century, where you had two really big schools of thought, Newton versus Dutch physicist Christian Huygens. Newton had what we call the crepusculary theory of light, where he thought it was a particle, where little particles of light come in and they bounce off of optics. And Christian Huygens had the wave theory of light. And Newton couldn't really reconcile wave properties of light with his theory. And come around the 19th century, you have the likes of Young, Fresnel, and especially Maxwell, James Clerk Maxwell, pictured here, who really demonstrated the wave properties of light, especially Maxwell with showing that both electric and magnetic fields behave as waves. And that's what light is. It's electromagnetic waves. It's electromagnetic radiation. And really, we see these properties all the time. You have refraction, what happens when light goes between different media, it deflects. Here we have, you drop a straw into a glass of water, you see it deflect, or I guess here's a paintbrush. Or diffraction, what happens when waves hit a boundary, or intimately linked to that, interference. I see that with light all the time. I have two waves, when their peaks and their valleys overlap with each other, I can either add, or if a peak and a valley overlap with each other, I can cancel and I get interference. I get destructive interference. And you can see that here. This is probably a helium neon laser, something red. And you see these fringes, you see these bright spots where you have constructive interference, and these dark spots, these dark fringes where you have destructive interference. Come around the 20th century, we have the birth of quantum mechanics, and I don't really want to out this physicist or this group of physicists because it's debated if they actually said this or not, but come the turn of the 20th century, they were kind of under the impression that, great, all of physics is solved. We made so much progress in the 19th century that, physics isn't really a fruitful endeavor anymore, and then the only thing you can do is just do more precise things. And I'm glad they're not, I'm glad that they are wrong, because I'd be out of a job. And you have the birth of quantum mechanics, and you had all of these different phenomena that were really unaccounted for, and just kind of these glaring problems. And really, the concept of quanta and quantization came to light to really solve these problems. The first one of them was the photoelectric effect, which was observed by Heinrich Hertz and then later explained by by Einstein, where if I shine light on a metal sheet, I'll eject electrons. And it doesn't matter what the intensity of the light is. If I have a really, really bright, intense beam and I shine it on this sheet, it doesn't really matter. What matters is the color. I can have a very bright or a very dim beam and it doesn't matter. What really matters is that what color it is. And Einstein said something has to be quantized. The energy that is arriving at this sheet has to arrive in discrete packets, and the energy that they carry is proportional to their color. And that kind of demonstrated that light has to be a particle in some way. And really, you can kind of think of the photoelectric effect like a pool table where I hit a pool cue and it hits another ball, and light carries energy and momentum even though it's massless. And we have this really cool concept of wave-particle duality where light is a wave, but it can behave like a particle, and things that are particles like electrons and other forms of matter can behave like waves. Macroscopic things like us, we're not good waves, we're particles, but if you throw me fast enough at a slit, I'll interfere. I'm not a very good wave. And the second thing is what we call the ultraviolet catastrophe. At that point in time, we couldn't even explain really what's going on with how hot objects like iron or, say, the sun emit electromagnetic radiation very well with classical theory. The idea, and well, really classical theory predicted that hot objects will radiate electromagnetic radiation and it's proportional to its temperature, or the intensity is proportional to its temperature. And classical theory said that this should kind of increase without bound. And I can have these very, very bright, very, very hot objects should just radiate all of their energy away and drop to absolute zero in temperature. And that doesn't happen. One of the thought experiments with that would be that the night sky would be infinitely bright if this was the case, because all the stars that we could see would just radiate all of their energy away. And Maxwell Planck, what's his name? Maxwell, whatever. Planck came around and kind of showed that the electromagnetic radiation that is radiated away from these objects has to be discrete. And really, you could argue it wasn't until the 50s in quantum field theory where the concept of what a photon is came to be. And the definition of a photon that I'm going to give you is that it's a quantum of the electromagnetic fields. And like I said, the energy that a photon carries is proportional to its frequency or its color. And it exists across a very broad spectrum that we interact with every day. We live in this very narrow band here that we call the visible spectrum, where the highest energy light that we see is in the violet and the lowest is in the red. We interact every day with, FM, AM radios, your 5G is out here. UV, that's part of the importance of things like the ozone layer. It absorbs UV. Ultraviolet light is very high energy and damages biological tissue. You move up to X-rays and you look at the size of them. They're kind of on the order of what we have for spacings of atoms. So you can use X-rays to probe the distance between atoms. That's a whole field called X-ray diffraction. And you move up here to gamma rays, and that's kind of like you either stand in front of a supernova and become the Incredible Hulk, or you die. That's the whole joke. The Incredible Hulk was hit with gamma rays and he got his superpowers. And on the other end, sorry, this is flipped. This was just how the image was, now going the opposite way from low to high, from left to right. I said that electromagnetic radiation is its color and its temperature are related. We kind of live here in the infrared at 300, and visible light is pretty energetic. It's kind of up here around 5,000 Kelvin, kind of near the surface temperature of the sun. And really, this will come in later when I talk about visible light, but room temperature, where we're at 300 Kelvin, is pretty cold to light that we can make very easily, like visible light. And really, it's here. You may not think of it that we are also radiating electromagnetic radiation. It's just in the infrared. It's outside of where we can see. But some things like snakes, they see in the infrared. That's how they image you, is they see the thermal electromagnetic radiation that you're giving off in the infrared. So I want to clear up some misconceptions about photons that kind of come up a lot. So it's not a stream of particles. I'm not going to take some snapshot of a laser beam and like zoom in, or if you have really good eyesight like me, you can just look really hard and see these little particles. They're not little blobs or globs of light. And really, it boils down to just being a really convenient picture for imagining some of the phenomena and describing it. And that's what a lot of physics really boils down to, is creating a convenient picture that may not be totally accurate to describe phenomena. And the real definition of a photon is that a photon is a quantum particle, and it is the quanta of electromagnetic radiation. And you'll see all these kind of different things where people kind of try to make it spooky, like, ooh, which way, if I send a single photon at 2 slits, which way does it go? And I think they're kind of trying to make it a little bit more mysterious than it really is, and really getting bogged down in this definition of it behaving like a particle and imagining it, and that photons are these little blobs or globs of light. So qubits, what you're here for. What's my favorite qubit? It's photons. But qubits, once again, classical bits, they exist as 0 and 1, but in quantum mechanics, we have qubits where it's a superposition of 0 and 1. And there's a really cool picture where you can say that any superposition of 2 states can be mapped to the surface of a 3-dimensional sphere. And you make a measurement, you pick some axis, and you collapse to your wave function to an endpoint on the sphere. And you have entanglement. What happens when I have more than 1 qubit? Do I have 2 spheres? No, I have entangled qubits live in 2 to the n space in a joint quantum state. And this is what gives us that exponential speed up, is that factor of 2 to the n. Now, this is where quantum computing wins in the end, is in this exponential scaling. And really the heart of really quantum computing is that, well, in comparison, classical computing, it's very hard to do problems that scale exponentially, but it's pretty easy to do with quantum mechanics. Not even a really, really good classical computer can simulate a moderately sized quantum system because it scales exponentially, and that's very hard for a classical computer to do. But building a quantum computer is hard. Why don't we have it already? In quantum mechanics, we have something called the no cloning theorem, which we can't copy a quantum state. That implies that we have to actually measure the state, and when we do that, we collapse the quantum state. And qubits are fragile. They interact with their environment. The environment can accidentally make a measurement by interacting with your qubits, and you collapse your state and you lose your qubits. And you also have this unique property with qubits, that you have a phase, which is really where's your state with respect to the equator, because there's a difference between being in the middle of the ocean, being in Kenya, or being in Indonesia, if I'm running around the equator. And so some of the requirements that you have, some of the criteria for qubits is, well, one, I need to be able to entangle them, and that means I have to have my qubits interact with each other. If without entanglement, I'm not going to get that exponential speed up. I'm not going to get that 2 to the n number of states. But I also need isolation, because if my environment or something else is interacting with my qubits, I can accidentally collapse my state, and we don't want that to happen. So really, it's a trade-off. I say it's a double-edged sword. You kind of have some trade-off between either being able to easily interact with your system or being able to isolate your system. And so I've thrown together kind of a not all-inclusive list of qubit candidates, and you can argue that superconducting qubits are the best for control, the best to interact with. And on the other end of the spectrum, you have photons, which are the best for isolation. And then everything else that you've talked about, I know Sarah gave a really great talk last week on trapped ions, and you have NMR, quantum dots, everything else just kind of falls in the middle, and they have their own trade-offs between isolation and being able to interact. Like, for example, trapped ions, they're isolated, they're in an ultra-high vacuum chamber, but they can interact with each other. They have the Coulombic interaction, which, yeah. So photonic qubits. I said they're really great for isolation. Photons don't interact with each other. I have isolation. There isn't really a straightforward fundamental interaction between photons. They don't have charge, mass. They don't really have some sort of fundamental interaction like that. And so, sorry, Star Wars fans, lightsabers aren't going to be coming anytime soon because of that. But light does interact with matter, which does give us some degree of control, which does give us control. And you can argue that atomic, molecular, and optical physics, AMO, at its heart is really using light to control atoms. And then my subfield, which is very intimately linked to that, quantum optics, is kind of the other way around. You're using atoms to control light. And it's also easy to encode states into photons. Probably the easiest one to think of is polarization. What orientation is the electromagnetic field, or typically we choose the electric field, oscillating? And you can draw a very similar picture to the sphere with the superposition for a qubit for the polarization states of light, where I can have them linearly polarized and they're just orthogonal to each other, or I can have my field rotating in time and it either goes clockwise or counterclockwise, or we usually call it left hand or right hand circular polarization. But we get a lot of information from light every day. We're really good spectrometers. We get information from light. We get information in time. I'm seeing things in real time. When I look at something, I get information from its color, and I get information from where it is spatially. And those are also degrees of freedom that you can encode for photons. You can have what we call time bin photons, where I know how fast my light is going and I know the path it travels, and I can have two different path lengths, and I can encode when does my photon arrive as that. I can have some people do a basis early and late, where a photon goes on one path or it goes to another that's longer. Yeah, or you can just do it in color. I have two photons of different color come, and that can be my basis. And it's also scalable. I'm in my apartment right now, but if I was to walk over to my lab and turn on my laser, with the power that I have in my laser, I can make on the order of 10 to the 17 photons per second. And there's a whole subfield, there's a whole field of technology that's called integrated photonics, which is like what you have with electronics, where you're doing things on chip, but doing it with light and transporting light on chip for, yeah, and that's already a commercial technology that's out there. That's modern computers run on that. It's not some really far off thing like people think quantum computing is. So it's a scalable technology too. And we have commercial optics. We know how to encode and manipulate the states of light for a very long time. I took these pictures in my lab, and a really cool colored beam splitter, and our very, very gnarly yellow visible laser bouncing off some optics. So why are photons good qubits? Well, first of all, light's fast. It's the speed limit of the universe. And light can travel extremely far without getting lost. Light travels 92 million miles from the sun to your eye, and even further from further stars. So please don't stare at the sun. It's not good for you. And so really, photons are really excellent for transmission. They're really excellent for transporting information. And when I showed that temperature scale, I said that visible light is very hot compared to room temperature, or room temperature is very cold compared to the temperatures that visible photons are at, and visible light is at. And really, I've frozen out when I say that quantum things are typically cold. Room temperature is very cold to a photon at visible light, visible colors, and it maintains its quantum behavior at room temperature, which is really great for transmission. I can just send light at room temperature in free space, and I'll still have quantum behavior. So rather than really talking about quantum computing and the regimes that you do quantum computing with photons, I really wanted to talk about where I think photons are more important, or where I'd argue that photons are more important, which is what we call quantum information, because I said that photons exist along this kind of spectrum of criteria for qubits. And photons are all the way over here for best in isolation, and everything else you've kind of talked about is over here. So the problems and how you do quantum computing with photons is very, very different. And I just kind of didn't really want to get into that. And really what I want to talk about is this main point, is that no matter what platform wins in the race to build a quantum computer, whether it's trapped ions, superconducting qubits, photonics is always going to be an extremely important, essential part of any sort of quantum technology. And so what do I mean when I say quantum technology or quantum information? What I really mean is harnessing and utilizing the quantum degrees of freedom of a system for typically these three purposes: communication, computation, and even precision measurement. And so what do I do with quantum information with photons? Well, if I have two quantum computers and I want to connect them, well, tough luck if I can't put them in the same cryostat or vacuum chamber. And if I actually want to communicate and transmit information that is quantum, I'm going to need to connect it somehow. And the way that you're going to do that is with photons. Light has a native interaction with matter, and I can send photons a very long way without getting lost. And that's how we're really going to build up these quantum networks. There's also this idea that, well, building a large-scale quantum computer might be very hard. So why not build a modular computer? I build a lot of really tiny quantum computers and link them together to build one larger quantum computer. And how are you going to do that? You're going to have to link them photonically. And how are we going to do that? I mean, photons. You're going to send it, your quantum information encoded in photons, and you can send them in free space or optical fiber, which you can kind of think of as a wire for light, except unlike a wire, one electron doesn't get all the way through the wire. There's other things going on. They collide, there are atoms in the way, other electrons, and it's some net current that gets through. But I can send a single photon through a very, very long optical fiber and retrieve it on the other end. And here's a picture my advisor sent me a while ago where there's an optical fiber that's being illuminated with laser light, and it's just coiled up on this platform. And like I said, there's a whole subfield called integrated photonics that's trying to do this on chips so it becomes a really big scalable technology. And so I kind of wanted to take this kind of last part and kind of boil it down to something really cool, not exactly really useful. We've been able to do it for a while, since like the 80s. It really kind of, most of the demonstrations have been done with photons. And it's just something that kind of uses the quantum weirdness for information and communication. And that's what we call quantum cryptography. So first, classic cryptography. It's based on not impossible tasks, but tasks that are really hard to accomplish. All classical cryptography boils down to is making it a very, to decipher something, it has to be a very, very hard, you want your security to be something that's very, very hard for a computer to do, but not impossible. So you have imperfect security, because if someone comes up with a way to efficiently do that computation, well, you're out of luck. Your whatever protocol you came up with security is, it's obsolete at that point. And another really key point is, you don't know in classical cryptography that you have an eavesdropper. You think that in World War II, that if the Nazis knew that people were working on cracking the Enigma, or when they did, that they would have kept the same code and wouldn't have updated it. Yeah. But in classical cryptography, usually in quantum information, we have two parties, Alice and Bob, and they're sending information to each other. And then you have this third party, Eve, the eavesdropper. I know we're very clever with our naming. But let's say Alice is sending information encoded in pulses of light of different intensity, and she's trying to send it to Bob. Eve just puts a 50-50 beam splitter there. And after that, she puts an amplifier with a gain of 2. Bob will still get the information, but so will Eve, and they'll have no way of knowing that Eve was there and intercepted any sort of information. And it's in quantum cryptography where this is totally different, and there's no way for someone to eavesdrop in a way that isn't intrusive and doesn't give them away. And so you're really providing security that's based on fundamental laws of physics. And we don't really mind eavesdroppers because we'll know if they're there or not. And really, it's based on the principle of measurement and the fact that you can't copy a quantum state. Let's say Alice is sending single photons, something that has quantum information, all the way over to Bob, and Eve puts a beam splitter there. Well, any sort of deciphering that Eve does is making a measurement. You can start with some wave function that maybe looks like this, but when she tries to intercept the information, she's making a measurement. She's collapsing the quantum state. She's changing it. In general, any sort of interaction for her to decipher the quantum information is intrusive and will collapse and change the quantum state. And Alice and Bob will know that. That's something that they can pull out. And that's what gives us the perfect security. And it turns out this isn't something that's really super useful, but all quantum cryptography kind of boils down to these general principles. And some higher order protocols and stuff like that are kind of interest, but this stuff has kind of been around since 80s, 90s, the idea of it. And it's been around for a little while. Great. So the second part was kind of the professional development side. I didn't really know what to put for this slide, so I just put pictures of the lab and of our new campus at Illinois. So what really got me into physics, I guess, ever since I was really little, I knew I always wanted to do science. I was like obsessed with Jurassic Park as a little kid, like not very atypical of like a little 5-year-old to be obsessed with dinosaurs. I wanted to be a paleontologist. Then in high school, I had lots of really great teachers, and I did the International Baccalaureate program in high school, and I had a really great physics teacher and a really great chemistry teacher. And we had this program where you could go and do biological research in Costa Rica and work with a PhD there and one of his grad students. And I did that 3 times. And that was really, really great. And that really got me interested in doing research in general. And so when I went off to college, I took physics classes and chemistry classes, and I majored in both, and I did research in both, back and forth. And my advisors and my professors there really kind of pushed me and really made me want to go on and pursue something in graduate school. And it was really how I ended up at Maryland due to my research advisor in physics in undergrad. We were doing solid state. When I told him I wanted to apply for grad school, he's like, hey, I think you'd really like the University of Maryland. So I put in an application. And so while I was at the University of Maryland, I worked for Elizabeth Goldschmidt. She was at the Army Research Lab, and this is our former postdoc, Hao Shan. He is now at a company in Colorado called Cold Quanta. But at the University of Maryland, we had the Joint Quantum Institute, or JQI, which was a collaboration between the University of Maryland and the National Institute for Standards and Technology, NIST. And we had a lot of collaborations with national labs because there were a lot out there, like the Army Research Lab. And that's really how I came to work with Elizabeth. That was actually by luck. I was with a friend finals week, and we went to go get breakfast, and she knew Elizabeth, and we bumped into Elizabeth and we started talking, and Elizabeth was like, I need a grad student. And I'm like, I need an advisor. And so we met later, I think probably the next day, and we just talked, and the rest is history. I've been her student for about 2.5 years now. Crazy to think it's been 2.5 years. But Elizabeth's great. She's like my physics big sister. She's around the same age as like my older brother, a couple years older than him and his friends. And then Elizabeth took a job at the University of Illinois, and that's where I am now. She asked me to join her. So at the time, I was her only grad student, so it wasn't like that big of a problem to transfer. So what do I do in my PhD? So one of the problems with light is it's hard to hold on to. It's moving. It's moving at the speed of light. But atoms are really good at storing light. They absorb light. And that's what my research is. It's storing single photons for some period of time. We call that a quantum memory. Mostly that's been done historically in atomic vapors, because atoms in gases, they don't really interact with each other. They're very far away. But we do it in solid state systems that are very, very cold. Here we are at 4 Kelvin, and our atoms aren't moving. They act like a frozen gas in this solid. And really what we're doing is just storing and retrieving single photons in really in an on-demand way. And right now our projects are kind of an intersection, like an intersectional study. When I was at Maryland, I worked with a chemistry group under Dr. Efren Rodriguez, where I was growing new materials in their lab. And here now we're working with Dr. Daniel Shoemaker in material science. He's growing us new materials for us to study. And really, I mostly just do things like characterization of these materials, especially optical characterization. And in the end, what I want to do for like my dissertation and stuff is with these new materials that we've characterized, show some sort of quantum memory protocol. I've shown that I can store and retrieve single photons on demand in an efficient way in these materials. So yeah, in March, we packed up our lab right outside DC and drove over the course of 2 days all the way to central Illinois. And we got there like 2 days before the shutdown happened for Illinois, for the state. And we were lucky enough to just have just enough time to take everything out of the van and bring it up to the lab and start getting things unpacked before quarantine. But now we're back on schedule, and I mean, we're still a bit behind because of quarantine, but everything's back and put together. And we're getting these brand new labs that are still under construction, and hopefully by next month they will be done. They built these labs from scratch. They did all the electrical, the plumbing, everything. We're gonna have these brand new fancy labs. Right now we're in a temporary space, and we were in a kind of temporary space at Maryland too, so it'll be nice to have a permanent home for our experiments. And all the new toys are getting installed. Like we're getting a brand new cryostat that's 1.7 Kelvin, even colder. And now I actually have a group. I'm not the only grad student anymore. We have Jean Long here, who's in his second year, Danielle, who's in her second year, my advisor, Elizabeth. And then we have our undergrad, Eddie, who's a senior. And so what do you really do in grad school? What's kind of your day-to-day thing? It's one of my favorite PhD comics. Being in grad school is like being in kindergarten. You do get lots of cookies at seminars. You're going to want to nap a lot. You do copy and paste a lot, especially if you're coding. But I play with lasers a lot. I play with lasers every day, and that's fun. In particular, I play a lot with cryogenics. Like this week, I was working with doing training for working with a liquid helium cryostat, and I have a video here. Down here is like where the sample is. It's like this little aluminum box at the bottom of the cryostat where you have these windows that look in, and you have this like 4-foot sample, like 3 to 4 foot sample rod that you push down into the cryostat, and you at the end of it is a piece of copper where you mount your sample, and that's what this little block is here that you can see. And we have windows because I'm gonna interact with it with a laser. I'm gonna probe it with a laser, but I took this video while the helium was still boiling. It was just about to hit 1.4 Kelvin and become liquid helium. Let's see. So you can kind of see in the windows the helium kind of violently bubble before it finally calms down and we can start doing physics with it. And I did this the other day, but I work with cryostats all the time in cryogenics, and liquid helium is kind of the difficult one to deal with, but also really cool. But as an experimentalist, in particular, I work a lot with my hands. You have to put together optical setups. You have to put your experiment together. I'm reminded a lot by, especially at JQI, by some of the faculty there that we have it so easy nowadays, because back in the day, if you needed more optics, you had to build it yourself. You had to make your own optics. And I live in an era where I can just buy commercial optics. We work with a lot of electronics, taking things apart. Usually you're doing new things, so you need to, take electronics apart, put them together, make them do what you want. And if you're working with cryogenics, sometimes that means working with plumbing, which can be very gross, but also like a good life skill to know how like plumbing works and doing kind of maintenance like that. I would joke that at one point when I started working for my advisor, I was getting the house water and our lab working, and I joked that I was just kind of the only plumber who has homework to do. The only plumber that has problem sets. You do a lot of coding. Coding and coding languages are really great tools to have at your disposal. When you have large data sets and things like that, you're going to need to sort through information, understand it, and present it. And you can do all great things like automate your experiments and things like that. So day to day, I'm probably using MATLAB more than anything, but if I'm solving problems and things like that, Mathematica, thumbs up. Python is great. And computers are ultimately your friend. Like, yes, I know a lot in courses in like undergrad, they want you to do it the hard way, the long way, so you understand what's going on. But eventually you hit a point where you're like, you get to class and you raise your hand and professor's like, what? And you're like, can I use Mathematica to solve this problem? And then the professor will say yes or no. But it's a good skill. It's something that comes in handy all the time. And I do a lot of writing. I do a lot of writing and presenting.
Can I interrupt there for 2 seconds? That just so that you know, students have free access through UCLA to Mathematica and MATLAB, so that I think you would.
It's great.
Right, to try them.
It's otherwise expensive. But I also think science communication is really important. So I've given talks before, like through the grad school at Maryland. Here, I was invited by my friend Anna. We were at Maryland together. I also do other forms of writing. I just had an article published, I think 2 weeks ago in the Huffington Post. And I've been talking with someone here about doing science outreach and science communication and writing. And I think it's important to be able to really make your field accessible. And that's a principle that I hold very dear. But ultimately, when it comes to doing physics, naps are key and coffee is essential. Those are kind of what grad students run on and undergrads. So take lots of naps and drink lots of coffee. I've already had like 3 cups of coffee this morning. So I'm still in grad school and I make the joke, what do I want to be when I grow up? Aside from being a paleontologist and stuff, like I'm still holding out that I could someday be Spider-Man or Batman, but everything else is plan B. So, like I'll ask people like that I know that are, like professors and stuff like that, are scientists I know who are doing like postdocs and stuff. I'm like, oh, so what do you want to do? What can I do? And the answers are kind of all over the place with physics, which is kind of a great thing, but also a little frustrating because you're given this broad spectrum and usually the answer is super vague for like, oh, what can you do with a degree in physics? And so things that I have been kind of looking at are things in industry, like being like an engineer or technician. I've talked to lots of engineers and technicians while building experiments and things like that. And you spend 90% of your time troubleshooting and talking to technicians, trying to get something working. And it sounds like a pretty neat job. Like you travel a lot, especially if you have something that's like really desirable. And it's a small company and everybody around the world wants it. You got to go and install it and stuff. And you get to go on these free international trips and stuff like that for your company. There's also working in government labs. That was something really great about Maryland, was just having all these government labs around and you can talk to people. Like my advisor who worked at the Army Research Lab, like and all these different collaborations. Or even on the other side, working in the private sector and doing research for some company. But if you do lots of coding and stuff like that and modeling, like that's a big part of physics, is you're developing a model to explain physical phenomena. That's being able to develop models and things like that's really important to things like finance. And that's actually a pretty sizable chunk of people. If you look at like APS puts out like a pie chart every now and then of what fields do physics grads go into, and finance is actually a pretty big one. And then, I mean, there's always academia. So my next stop would be, if I was to go into academia, I'd have to do a postdoc but I do enjoy teaching. I won some TA award when I was at Maryland. I'm a TA now. I like doing talks like this and educating people about things. So who knows? So I kind of wanted to end this with a last slide. Advice that I wish I had when I was a freshman. Not just about physics, but just being a freshman in general and life and going forward. There are no dumb questions, and just ask questions. That's what your professors are there for. That's what your TAs are there for. So just don't be afraid to. I can't iterate this enough. Ask questions. It's okay to admit that you're wrong. That's just kind of that's to me is a big step in personal growth, is just being able to admit you're wrong, and you learn something from it. And admitting that you don't know something, that's totally fine. I know, especially in academia and stuff like that, there's this pressure to feel like you know everything, and it's fine to not know everything. There's so much out there. And that's part of just asking questions, is like, I don't understand this. I don't know this. I got this answer wrong. I'm going to ask somebody. And really, that's why I put this Niels Bohr quote, because really you become an expert when you learn every single failure mode of something. And that's something that my advisor tells me all the time, that if I'm trying something and I don't think it works, she's like, did you try everything? And usually when it's you try everything and you figure it out is when you start to figure it out and understand it. And so ultimately, learn from your failures. That's important. This next point is just kind of like in general, but time is fleeting. Make the most of it. Even in undergrad, even though I was in STEM, I was able to do things like study abroad and things like that. And that's where I took a lot of really great physics courses and stuff like that. And yeah, like you can have opportunities come before you and take them. You're in college once. College is only 4 years, and you'll very rapidly see that your time's running out when you're there. And I feel like I blinked and I was just graduating from college, and now I'm in my 4th year of grad school. So make the most of your time. Just have fun, do what you love. And this is kind of like a more pedagogical thing, but learn to learn. I had a late professor at my undergrad. Like my generation, we were his like last round of students, and he really pushed us. And he had classes that we had to take that were all really project based, and a lot of times it felt like he was really throwing us into the deep end. And really the most valuable thing that came out of that was we had to learn, if that makes any sense. We had to teach ourselves, how do we personally learn things and kind of hone that skill and be able to take these advanced topics and teach ourselves. And that's what a lot of grad school is that nobody knows what they're doing. You have to figure out these really complicated, very difficult topics. And part of knowing how you learn and how you absorb information is really important, because at times it can be really, really difficult, paralyzing to sit there and have this really complicated problem that you have to solve, or this really complicated subject that you have to know something about. And just being able to understand yourself and how you learn things can really help. And ultimately, I get this philosophy from an old coach of mine. Practice makes permanent. When I was younger, I did martial arts, and my instructor used to tell us he didn't like the phrase practice makes perfect. He liked the phrase practice makes permanent. So if you have bad habits, it's going to be harder to kick. If you have good habits, they will stick with you. And I know from experience, like my friends and I, when we were especially freshmen. We'd have problem sets due for our physics classes 9 a.m. Thursday morning, every Thursday. And we would just meet up 10:30 p.m. to as late as midnight on Wednesday and be like, hey, did you start the problem set? No, do you want to work on it now? And, you know, it was a bad habit. It was a very bad habit. But as you start practicing better habits, you know, they'll stick with you. And I think that's about everything. Just wanted to thank you guys for having me. And I wanted to thank the Army Research Lab for funding us, Maryland and JQI, Illinois, and the Material Research Lab for letting me take videos of the cryostat. And my lab mates, it's great to have lab mates, and you know, my mentor Elizabeth and former mentor Haoshan for being really great. And you guys for having me here, and Anna for inviting me. Yeah, questions, comments, concerns?
Thank you so much. That was really good.
Thank you.
Thank you for the great talk. I really enjoyed it.
Thank you.
I want to ask you, are there some notable experimental things, how can I say that, that show interaction, perhaps creation of entanglement or creation of some, I'm sorry, gates with light?
Sure. So actually, one thing that's been around for quite a while, nonlinear optics. You can have these photon pair production processes that happen in nonlinear materials that give you pairs of entangled photons, one of which that's really important is called spontaneous parametric down conversion, where you can make entangled photon pairs. And that's been around for a while. And actually right now, one of my lab partners, Jean-Long, is doing, he has an experiment going on where he's doing that and making entangled photon pairs. But the whole, that's a very big part of nonlinear optics, is that nonlinear materials are famously nonlinear, and they have an interaction with light that can give you entanglement. It's like an indirect way of having photons interact.
Thank you.
Mm-hmm.
Perhaps another question. In your
Sure.
research, that somehow you create quantum memory with light.
Yeah.
How long can it stay usable?
So the upper bound that people have been able to demonstrate for storage, I'd say, is kind of on seconds, but upper bound for like what people have shown for potential storage could be hours. In ours, we talk about a coherence time. How long can you hold on to your quantum state? And the longest coherence time demonstrated in the materials that we work with in particular was shown by our collaborators at the Australian National University. And the longest to date is 6 hours. They can't store for that long, but that's kind of the upper bound on how long you can store. And they think even in their paper, they acknowledge that they think that they're missing factors of 2 somewhere in there, and it could potentially be longer than that.
Thank you.
Mm-hmm.
Can quantum computers be hacked?
Can what? Can quantum computers?
Can they be hacked?
Can they react?
Can they be hacked?
Can they be hacked? I don't know. I mean, at the point that we're at with like the point in time where we are in the history of quantum computing. We're still figuring out how can I physically build one of these things, and thinking about computing in a really fundamental different way. I mean, I think with like quantum cryptography, you could have it where, you know, someone tries to, you know, steal your quantum information, but most of those protocols work on some general principle of measurement where I'm going to know if somebody's trying to steal my information or not. One kind of cool thing you can do, I forgot to mention this, but last week Sarah talked about like their kind of cloud-based quantum computing at Honeywell, where you send them a computation that you want to do and they send it back. Photons will work for what we call blind quantum computing, where whoever's doing my quantum computing for me, whoever I'm sending it into the cloud to, I don't want them to know the information that I'm sending. I don't want them to know what calculation I want them to that I want to do. So I have to send them a quantum state. I have to send them quantum information. They do the calculation, and then they send the result back encoded in quantum information, and it's completely secure. And so I kind of privately send them what I want. They do the computation and they send it back, and it's been perfectly secure, because if anybody interacts with it or measures it, I've destroyed my quantum state. So I would say with like cryptography and things like that, it'd be a pretty difficult thing, like with the way that quantum cryptography works at its core.
Oh, very cool. Thank you.
Yeah. So I saw a random question. Is the photonic quantum computer actually the cheapest? That's kind of debatable. Because one of the problems with building quantum computers with photons is if you're going to do it with linear optics, you're going to need it. That's kind of the problem with scaling it, is that you're going to need all these linear optics, and those are very expensive, very, very expensive. And if I'm going to need lots and lots and lots of qubits, I'm going to need a lot of these optical components. And yeah, that's something that people are trying to kind of tackle. Yeah, yeah.
I have a question.
Yeah.
So I'm a computer science major, and I just want to know like how computer science is implemented differently in quantum computers versus classical computers, and like what the applications of computer science are going to be in the future when quantum computers become more widely used.
Sure. So have you talked about like P and NP type problems, like where P problems are problems that scale polynomially with the size, and then NP problems are problems that scale exponentially with the size of the system? That's kind of like where classical computing and quantum computing diverge, where classical computers can do things that scale as a polynomial. Like if I have a system of size n, the problem might scale as n to the fourth, and I can do that. And I might have a problem that scales with the size, exponentially with the size, like e to the n. That's something that is actually really easy to do with quantum computing, because the quantum states, when you entangle qubits and things like that, scales as exponentially. And that's really the regime where, in the end, quantum computing will be able to solve problems that might be very difficult for a classical computer to do, like things that scale exponentially. One example, I like it, one of my postdoc friends gave it to me, is the reverse phone book is a problem that was easy for a quantum computer to do, but not for a classical computer. It's easy to look up someone's phone number by their name in a phone book. Like, I haven't seen a phone book in like 20 years. I don't see those anymore, but it's very hard to look up somebody's name from their phone number. there are lots of problems like that that can be solved that are what a quantum computer is ultimately kind of the goal for. Does
Gotcha.
that answer your
Thank you.
question?
Yeah.
Yeah.
Hi, I have a question.
Yeah.
So I remember you said you did both chemistry and physics in undergrad, and I'm a physics major right now, and I'm also like considering doing that, and I'm also leaning towards like atomic and molecular and optical physics. So like,
Sure.
what do you think were there any like benefits in doing like the chemistry degree specifically in relation to your career?
Yeah, I mean, I've been able to do collaborations where I've like where I've tried growing my own materials, and especially when I've taken classes, especially kind of on the optics and side and stuff, like the physics gives me a better insight into the materials and understanding really what's going on, especially because especially like in chemistry, we didn't really dive really into things like spectroscopy and things like that. What's really going on? What's the mechanism behind this and why materials are the way they are? And that's really where the physics came and kind of gave me that background. And that's something that I've always really enjoyed, is being able to kind of take the chemistry and the things I think are really cool and be able to dig a little bit deeper and understand it a little bit more on a fundamental level that you don't really get to talk about a whole lot in chemistry, because there's so many other things that you have to talk about in chemistry. But one thing that I took a class, I took a graduate chemistry class last fall, and I really enjoyed it because it was kind of the intersection of that. It was called molecular symmetry and bonding, and it was really kind of getting into the weeds of where does quantum mechanics come in when talking about chemical bonding and bonding theory, and really explaining some very interesting behavior that you don't really talk about in chemistry because it's just kind of far out there, or it's kind of beyond the scope of what those classes would cover. And I just found that to be really cool, because some things that I would see in chemistry that were maybe exceptions to rules that you learn, like orbital filling and stuff like that, and seeing the exceptions and really understanding where they come from a fundamental, like from a really fundamental perspective.
Okay, thank you.
Yeah. Anybody else? I mean, I've had a great time. Clarice, you have a question?
I have. I would like to take quantum computers a little bit out of the lab. Can you maybe comment, like in the future, what would it do, say, to the world if, say, some countries had access to quantum computers and some countries did not have access to quantum computers? In other words, like, what effects can this technology have in?
I think one thing in particular will be things like cryptography. Like the way internet security and stuff works now is classical. And that just means that the problem is hard to solve, but not impossible. And I think it'll also really help. I think like things like national security, things like that. And you're going to want to, if you have a quantum computer and you can transmit quantum information, that's probably the avenue that you're going to want to go with, like things like national security, so you don't have, hackers and espionage and things like that. And I still think that's kind of down the line. Quantum cryptography has been around for a couple decades now, and it hasn't really piqued anybody's interest. Like when it first started coming around, everyone's like, yeah, this is a really cool idea. And when they started demonstrating, they're like, yeah, that's cool, thumbs up. But I've found that a lot of people aren't super interested in it anymore. And yeah, I mean, I think that's kind of the route my mind goes to when I think about like who would benefit from quantum computers or not, like as a disparage between like, as like a, as something like that a really wealthy country might have versus the rest of the world. And I mostly think of it in terms of like security and things like that. But that's how I kind of got into the like liking my field, is because somebody told me about, you know, quantum cryptography. This is fundamental security based on the laws of physics. And I'm like, that's so cool. And that's kind of where my mind goes when I think of really where are some of the applications going to go that are kind of already been around and here.
I have a question. Sorry. Okay.
Yeah.
I have a question relating to like, I guess like maybe coursework. So I'm a biophysics major and I'm
Sure.
very interested in the math minor.
Sure.
I'm taking, like right now, I finished multivariable last quarter. I'm taking linear algebra
Okay.
right now. Were there any math courses that maybe were outside of your major that you took, or that were in your major that you took that you thought really helped you with your physics path particularly, or your chemistry?
Yeah. Particularly linear algebra. Quantum mechanics is written in the language of linear algebra. Linear algebra shows up all the time, especially the eigenvalue problem. Like like pretty much all of my classes, like in graduate school, it's like, all right, we come to the conclusion that this boils down to the eigenvalue problem, and that's what you do. Or multivariate calc was very useful. Some things like differential equations can come in handy. If you go into like things like theory, taking classes in analysis really help, because a lot of people in like particle physics and stuff like that in theory use complex analysis a lot. But yeah, I would say like if I had to pick one, linear algebra, like that was probably the most helpful of all the classes, because when you take quantum, you're going to sit there and you just see it and you're like, this is linear algebra.
Yeah, the math minor at UCLA is very flexible. There's like you just have to pick 5 upper dips. So I was curious, like if I chose it, like which 5 I should do.
Right.
So I think that's good. Thank you.
Yeah, of course. Oh, I see one question. It was asking me about my master's. No, I applied directly to the PhD at Maryland, and then I kind of left with my master's because my advisor's like, hey, I'm moving to Illinois and I want you to come with me. And so I was able to leave with my master's, like I was already on the PhD track. And my master's is just a master's in science in atomic, molecular, and optical physics. And yeah, so Fiat Lux, let there be light. That was also my undergraduate's university slogan, which was brought back memories. Yeah. Well, thank you guys for having me. This has been really great. I love answering questions and getting people interested in this field. And yeah.
Can we unmute ourselves and clap?
Yeah. Thank you.
Thank you so much, Donny. That was great,
Yeah.
great talk.
Thank you for having me.
Yeah, no. Hopefully we'll get to hear more from you sometime.
Yeah, maybe I'll have some data next time.
All right. Well, thank you everyone also for making some time on this crazy week to join us.
It's what, Tuesday, part 4. This whole week has felt like a year.
The memes on Twitter are pretty funny though, about like Nevada.
Oh yeah, Nevada's gonna show up to class 2 hours late with a nice coffee.
And maybe when things are normal here again, like we can invite you, Donny, to visit UCLA.
That'd be really great. I got a lot of friends in California from Maryland too. It'd be nice to catch up. Great.
And then
Well, thank you so
what's
much for
next
having
week?
me.
Oh yeah. I will be talking next week about quantum computing with atoms. So yeah, stay tuned.
And well, thank you so much for having me. It was really great.
Thank you so much. That was wonderful.
Thanks.
Thank you, Donny.
Bye.
Thank you.
Thank
See you
you.
all. Say bye, everybody. Say bye.
Bye.
Bye.